So for this station, we are going to look at filtration. And what we're going to do is that I'm going to take a beaker, I will take a funnel, and also a sample of filter paper. And the way you do this, you want to fold the filter paper all the way down into like eighths. So kind of like that. And the entire idea to do that is, or the reason behind doing that is because we don't want to just like push this in, because then you can potentially cause for it to rip. And obviously that defeats the whole purpose of filtration, right? So once it's like this, you fold, and it kind of like forms a funnel. And depending on the size of your funnel, it may or may not fit. So like right now it doesn't fit completely. So what I'm gonna do is I'm gonna make another fold, and then I'm gonna double fold it, so kind of like that. So the regular, and then another one little here on the side, so that hopefully it fits better. And now it does. And you would just continue doing that until the filter paper fits completely flush in the funnel. And that's just good practice, guys. So don't ever just like push in. So we're gonna take this, and the entire idea here is that we are going to take some properties of our sample. So we have some sand at the bottom, some dirt, and then some floating debris. And for this separation technique, what we want to do is that we want to use the fact that some of the debris is a solid, so the filter would stop it. And the filter, basically what it does is that it allows the liquid and some of the really, really small solids to go through, and the larger stuff gets stuck in the filter. So it's not necessarily like a 100% you're going to filtrate all of the water. There's actually different levels of the filters. So this one I would say is like a pretty average one. But what we want to see here is that the water's filtrating. You can see that it's still very murky. And the reason for that is, like I said, some of the debris is really, really small that is able to go through the filter. So we have the filtration taking place. I'm going to show you guys from the top. Oh, it's moving. Don't move. And then from here in the top, the water is going through. Some of the small solid is as well. So that would be actually one of our limitations. It does not 100% stop every single solid. So if the solid is really, really, really small, it's still going to go through. So you can actually continue to do your filtration this way, and every time get better and better filters. So like the one I use is a pretty standard one. This one is qualitative filter paper. So it's going to be a little bit better than the one I use. So if I was to filtrate this first and then use this, what I separated, into another filter, this one, or even better filters, because this is not the best out there, you would over time remove most of the solids. So that's one of the other techniques. And of course, once this entire filtration takes place, we would want to separate our solids from our liquids. Okay guys, so this is the station number 7 for coagulation. And what we are going to do here in this particular lab, so we're going to take a beaker with some water in it, and I poured just a small amount of oil. You may be able to kind of see the small droplets right there at the very top of the beaker. So we have the oil already in here. And what we're going to do for coagulation is that I'm going to take some scoops of sand, I'm going to drop it into the water with the oil, and then I'm going to stir. Now, the entire idea here is that the sand is going to absorb some of that oil. And that's exactly what I'm doing right now. Just pouring in. This is going to start absorbing some of that oil. And over time, as we stir, hopefully you guys will start to see that small droplets that look like droplets of sand start to form. And I do have another example that's already coagulated that we did earlier in class today. Okay, you can kind of start to see you see the sand at the very bottom. It's more dense, obviously, so it's going to drop to the bottom. But hopefully you guys can kind of see in here at the very bottom, some of they look like round circles made of the sand. I'm just going to continue to stir. And I'm going to, okay, so I'm going to show you guys our other sample that we did in class today that has, you guys can kind of see the circles, right? So the sand is like in little spheres, and that shows you that the coagulation has taken place and that some of that oil has been removed. Obviously, if we wanted to completely remove the oil, we would have to take out some of that sand and continue to coagulate more and more and more and remove some of that. Now, here's the properties that we're looking at are going to be our absorption, right, of the oil. And it's important to note that one of the limitations is that it's actually really difficult to remove some of that coagulation. So you really have to do it multiple times. And I really don't know if you guys can see, but it looks like if it was like gel balls, like little spheres. And that's the coagulation that has taken place. All right, so in this station, we are going to look at chromatography. And what we are trying to do here is take a small sample of ink and use the particle size and the polarity of the ink itself and the different components of it to separate them out. So what I'm going to do is take just a plastic cup. I will take some filter paper that has already been pre-cut for us. And I'm going to take a marker, just a marker. And I'm going to draw a small dot at the very bottom, just like that. What I will do then is going to be place it, oh actually no, I need to get the water first. So we get a little bit of water, just enough to kind of cover the bottom of our container. And then I'm going to place this. So this is the tricky part, because if you don't do it right, this entire paper will get wet and then nothing will take place at that point. So I'm going to take a little bit of tape and I'm going to place it all the way at the bottom, barely touching the water, like barely. Because what I wanted to do is I wanted to have the water be absorbed and for it to go up. And what it's going to do is that as the water starts to travel up, right, up, what it's going to do is that it's going to start separating the components, right, so the ink, the particles themselves. It's going to start pulling them apart. So you should ideally see the, what is it called, the different colors that, oh no, I put too much water. Okay, we're gonna have to do this again. But that's actually good practice. What we will do is that just do another one. And so that way you guys can see like the way it's supposed to be and the way it's not supposed to be. So, and again, guys, this is chromatography. Now, of course, one of its main limitations is that this only really works with like things that are liquids that have different polarities. That have components that have different polarities, I should say. Okay. So hopefully this one will look a little bit better because I completely messed it up, the first one. Just a little bit more water. And you can kind of see on the first failed attempt that the reds are kind of like at the bottom and the blue ones are the ones that are going up. On the second one, you can kind of start to see the separation of the colors. I'm going to try and get this closer to y'all. But I think you guys can kind of see how the colors are indeed separating. This one takes quite a long time for it to completely show that distribution of the colors. But I think you guys kind of get the point of what is happening here. Alrighty, let's, I'm gonna leave it here and then I'll show you guys later on what the result is. Alright, in this station we are going to look at sifting or sieving. I'm not quite sure. I've seen it online and I've talked to people and they call it both ways. But it's basically, we are taking a mixture of solids that have different components that have different sizes. So what we're gonna do is separate them by their size. And what I'm gonna do here is I'm gonna take some weigh boats. And I already know that in here I have some pebbles, I have sand, and I have salt. So that's what our sample looks like. Ooh. So what I'm gonna do is take some of my, what are these called? I forgot the name. Anyway, so what I'm doing is I'm pouring some of my sample, and because I understand that there's a difference in the size of my solids, some of them, the larger ones, right, are gonna stay at the top, they're gonna be separated. The smaller ones that are able to go through are going to be collected at the bottom. But obviously this does not completely separate my samples. So what I'm gonna do next is take another sifter that has smaller openings, right? So I'm gonna do exactly the same thing one more time. I'm gonna pour it and then I'll let you guys see it. So I separated my, I separated my larger rocks, right? Then I'm gonna do the next set. So there we were able to separate into a smaller size of our solid. So ideally what would happen is that we would have gradually more and more, like, well, I should say smaller and smaller openings, so that over time we would separate them into completely their different sizes. Now the limitations for this is that, of course, what happens if you have something like salt, sugar, and sand? They're roughly the same size, so it would become really difficult to separate all those three from each other because, well, they're roughly the same size. So there's limitations to it, and again, the properties that we're looking at here is the fact that they are solid and that they have different sizes. Alrighty guys, in this station we are going to look at magnetism, and what I'm going to do is that I'm going to take a solid sample of my mixture. Now for magnetism to work, is that at least one of the solids has to be attracted to magnets, right? It has to be a metal that has magnetism to it. If none of your metals, or if none of your metals or none of your samples has magnetism, well, it won't work, right? So that's one of the limitations. So we're looking at solids. We're looking at solids of roughly the same size. So therefore, like, separating them by size wouldn't really make a difference, but we can use magnetism. Now the key here is to use a magnet, right? And I like to put them in a bag because if you look at the sample, it's powder. Imagine trying to remove all those tiny little pieces of metal from the magnet. So what we're going to do is, is going to be pour some of my sample, and I will show you guys in just a moment. I just need to move the camera back. So what I'm going to do is that I will pass over on my sample, right, with my magnet, and what we should observe is that attraction, right? So that's what we have. And over time, you continue to do this with multiple metals, right? And you can actually separate your samples. And in here, I'll tell you what I have is just iron fillings and sand. I put sand in here. So you can separate this. Trying to use a different method for this particular section would be pretty difficult because, like, again, the sample sizes are pretty similar. So trying to separate the sand from the iron fillings without a magnet would actually be a very complicated task. And then what I'm going to do for the kind of like to separate them from the magnet, and that's the reason you have a bag, is just remove the metal, right? The magnet, remove the magnet. And that's pretty much it for magnetism. In this station, we're going to look at electrostatic. attraction. So what I'm going to do is I'm going to show you guys, have my container, right, my watch glass, and my sample. And in here, again, is one of those samples where it would be really difficult to try and separate it by the size of the solid, because what I have in here is sugar, salt, and pepper. And I'm sure you guys have seen both, all three of them, and you know that their sizes is pretty similar. And none of the three is attracted to magnets. So it would be really difficult also to use a magnet to try and separate that. So what I'm gonna do here is I'm gonna take a sample, and I'll show you guys in just a moment. I'm gonna take a sample, spread it out on the watch glass. And then I'm gonna create a little bit of static. So what I'm gonna do is I'm gonna take some plastic straws and a balloon. There's fancier ways that we can create some static other than this, but this one's a pretty effective one, and it doesn't take long. So I'm counting here that at least one of my solid samples is attracted to that static. So I have my two straws, and what we're going to do is that we are just going to pass them over. And hopefully you guys can kind of see that we have some attraction already taking place. If you can see here on the straws, there is that attraction. I think you guys should be able to see how the pepper is the one that is attracted. So this would obviously take quite some time to separate completely, but you would be able to separate them regardless. It would just take a long time. And like I said, this is not a 100% effective way of separating, because you are relying on that attraction. So you can kind of see it. Like I said, it takes a while. So that's actually one of its limitations. It's a very, very long process of separation. And of course, you're also counting on the fact that at least one of those solids would be attracted to that static. All right, so in this station, we're going to look at evaporation. Now, evaporation technique for separation is one that is very useful, but it does have limitations. So the idea is that you would place you would place your sample that has your solid that's already been dissolved. And what you want to do is you want to remove the water. Now, evaporation is different from distillation in the way that evaporation, you're not going to collect that water. So let's just say that you really don't care for the water. You're just going to let it go. So that would be a good, evaporation would become a good separation technique to use in this case. So what I'm going to do is I'm going to take and I need to turn this on. I'm going to take my evaporating dish, and what I will do at this time is just place a small sample of my mixture. So what I have here is water and copper nitrate. Take a little small sample of it, and what I'm going to do is just allow it to go through evaporation. So all the water will boil away, and I should have at the very end just my solid sample. And this actually takes quite some time, so I'm going to in the video just kind of like fast forward it. So that was about 5 or 6 minutes, and we are almost to the point where we are done with the evaporation. And as you guys can see, it's still going, still boiling that water. And as you can also notice, the color of it has changed quite significantly. Right now we're about to finish up. We have our solid. Did you notice how fast that took place? And then that right there, what is left, And I better move this because otherwise it's gonna start burning. What is left on here is going to be the solid. Now, ideally, actually, guys, you would want to have done that a little bit sooner because some of my sample is burning now. But there it is, all of our solid sample that originated from our mixture that looked just like that.